We're going to end our discussion of carbohydrate chemistry with a very brief look at glycosidic bond formation. Remember, glycosidic bonds are the key bonds involved in disaccharides, oligosaccharides, and polysaccharides that we've been discussing. Glycosidic bond formation is an enzyme catalyzed process. And remember, it's in a coupling reaction that brings together two sugars. One of these sugars is going to be a nucleophile, and the other will be an electrophile. And so just like every other organic reaction, there's a nucleophile and electrophile involved. In this case, it's two monosaccharides. The nucleophile is a hydroxyl group on one of the monosaccharides, and the electrophile is a glycosyl phosphate, such as glucose 1-phosphate that you can see here. Why phosphate? Because it's a good leaving group, so that anomeric hydroxyl group has been transformed into a phosphate ester. In a few webcasts, we're going to actually be discussing more of the phosphate chemistry, the bioorganic phosphorus chemistry. But basically, this is a good leaving group, and it makes glucose the electrophilic partner for the glycosidic bond that's formed in the disaccharide sucrose. So fructose is the nucleophile. Its hydroxyl group at the C2 position is what's going to serve as the nucleophile. Now, a key part of the mechanism is, again, that there's a retention of stereochemistry, and so notice we start with the alpha glucose 1-phosphate, and we end up forming the alpha configuration at glucose, and so there's a retention of configuration, and the way that we might anticipate that that would come about is by a double inversion. We first invert, then we invert again, and we're back to the configuration that we started with. And in fact, that's how these enzymes operate. Again, I'm not giving you the full details, but you could imagine that the steps involved that oxocarbenium ion intermediate, and so with an enzyme active side chain that can serve as a nucleophile, the oxocarbenium ion beta phase would be protected to form initially this covalent adduct with an enzyme side chain. Phosphate forms the good leaving group to allow that chemistry to take place. Fructose, probably by a general base, is then activated and another oxocarbenium ion formed, its beta phase being blocked by this covalent linkage, but when it does form, the alpha side would be accessible to the nucleophile fructose, which come in and attack to form that alpha linkage.